Greetings, students. Mr. Keister here with you again today. We're going to continue on in Unit 12.2. Let's fix this screen just a little bit there. There we go. We're going to continue on today with Unit 12.2 and talk about a new K. Actually, we have two more to go, one today and one next lesson. Today we're going to talk about the equilibrium constant for weak acids, that is called Ka. And then the next lesson we will hit weak bases, which is Kb. As I look behind me here, had we been in school, Chem 2, this would be Friday the 8th of May. So as you can tell, we're getting very close to the end. Honors Chem, you would be actually a few days behind that. So anyway, we talked in the last lesson about the Chatelier's principle and how changing the conditions of equilibrium that our equilibrium reaction is run at can affect the value of K, and thus the formation of either more products or more reactants. Those same principles, Le Chatelier's principle, is good for any type of equilibrium situation, whether it be Kc or Keq, the general equilibrium constant, Kp, or, as we're going to talk about today, Ka, and tomorrow and next time Kb. So again, this we are not really following, but again, you should be, as I've said many times now, you should be referring to the modified Do-Nows / calendar document that is located on my homepage, on my Canvas homepage. So let me pull up our notes there today, and we'll get started. Now today, you would have received this handout, which is the Ka and Kb values of common weak acids and bases. We're going to be referring to that here very soon. We'll also be referring to it in our next lesson. All right, so we get started here. Freeze up the screen, or I should say unfreeze up the screen. There we go. All right, so equilibrium constants for acids and bases, and today we're going to talk about acids. So first we want to talk about what it means, or reiterate what it means for an acid to be strong as compared for it to be weak. So an acid is referred to as either strong or weak depending on the degree to which it dissociates or ionizes. All right. A strong acid, and we mentioned this when we first looked at our unit on acids and bases, which I believe was Unit 11.1. There were 7 strong acids that we learned: hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, chloric, and perchloric. Those 7 acids ionize completely, or 100%, when dissolved in water and put in solution. Notice, and so HCl I used as our example here, notice that HCl, that in the dissociation of HCl, we do not have an equilibrium situation. Why is that? Well, if we did, that would mean these would reform into hydrochloric acid. And in the case of the strong acids, that is not true, all right? These ionize completely, all right? So this solution contains 100% hydrogen and chloride ions and no intact HCl molecules. Let's take a look at that a little more closely. I have a question here that says, what would the magnitude or the value of the equilibrium constant K be for a strong acid? Well, let's take a look at that mathematically, shall we? So I'm just going to very kind of shove it in here, do a little bit of an ice chart here for this reaction, even though, as we can see here, it's not at equilibrium. It just goes to forward reaction. So let's say we start out initially, for example, with 1.00 molar HCl. So initially that would be 1.00 molar. These, of course, initially would be 0. As the reaction then occurs and goes to completion, here's what ionizing completely means. At equilibrium, if we had an equilibrium established, at equilibrium, there would be no intact HCl molecules remaining. In other words, all of them, however many there were, would be ionized to hydrogen ions and chloride ions. So as we see here, our change then from 1.00 molar to 0 is a reduction of 1.00 molar. All right, just looking at the general principles of equilibrium here. Well, if these are all in a 1:1:1 ratio, which they are, then that means these would have increased. Remember, reactants disappear, products appear. These would have increased by the same amount since the mole ratios there are all the same. And so at equilibrium, we would have 1.00 molar hydrogen ion and 1.00 molar chloride ion. So let's set up a K for that, shall we? So K then, we haven't really named it yet, but it is actually called Ka. All right. So K would be equal to the concentration of hydrogen ion times the concentration of chloride ion over the concentration of HCl. These are all solutions, so they would all be included there. So 1 molar, what would go on the bottom? Uh-oh. Hello. 0. Okay, those of you that are thinking math this early in the morning, it's actually quite early, and you see that, what does that mean in your math classes? What happens when you divide by 0? We get that term. That term, what is that term? Undefined. Well, mathematically it is undefined, all right? Let's talk about that answer, though, chemically, all right? Chemically. So let's use this as an example, all right? Let's say we had however many, a kajillion HCl molecules, all right? What if only one molecule out of that kajillion, all right, one, remained unionized, all right? So we had these two numbers here would be one molecule short of a kajillion, all right? And this, of course, would be one molecule, all right? So what's one molecule short of a kajillion times one molecule short of a kajillion divided by 1? Well, let's see. One molecule short of a kajillion times one molecule short of a kajillion would be a couple of molecules short of a kajillion squared, right? Right? What kind of a number is that? Well, I would call it huge, gigantic, ginormous, whatever term you want to throw in there. All right? So, can we actually define it mathematically? No, it's undefined. All right? But what does that mean here? Well, I hope you understand that undefined means that it is infinitely large. It's big, all right? So the K value for a strong acid is big, all right? Let's take a very quick, we're going to come back to this again, But let's take a very quick look at this chart. All right, just a very quick look. So as you scan through it, it lists a bunch of K values for all these acids. I want you to look at the first four they have listed there. All right, perchloric acid, sulfuric acid, hydrochloric acid, and nitric acid, which are 4 out of the 7 strong acids. What do you see there for a number under K? Well, there isn't one. What does it say? One word only. Large. Big. Ginormous. Gigantic. All right? It's infinitely large. We can't define it mathematically, but we do know that it is big. Okay? All right. Let's compare that then to a weak acid, shall we? Let me advance this here. So a weak acid, which would include any acid other than the 7 we just talked about, only slightly ionized in solution to some degree. All right. So here's one of them, acetic acid. All right, acetic acid. If this solution would be 5% ionized, all right, which would mean 5% of its molecules at equilibrium would have ionized, the other 95% would have remained unionized. All right. Let's look at that as an example. All right. So first of all, we see that our equilibrium arrows have returned since we're now using a weak acid. Again, let's just shove in there a very quick ice chart. All right. If this was 1 molar, our acetic acid now, and these of course started out at 0. And according to this particular example, if 95% of those molecules remain unionized or undissociated, then that means at equilibrium 95% of 1.00 molar would still be unionized molecules, which would be 0.95. Right, 0.95. Which means this would have decreased by 5%, or 0.05 molar. All right, which means these would have increased by 0.005 molar. Again, 1-to-1 ratio there between all the substances. And so at equilibrium, these would be 0.05 molar to 0.05 molar. And if you set up a K for that, as you can see, it would be, I won't write out the K expression, of course it'd be these two, concentration over this one. But it'd be 0.05 times 0.05, or 0.05 squared, divided by 0.95, which is going to give us some smaller value, much smaller, actually, all right? So I want you to see the difference mathematically that exists between the K of a strong acid, which ionizes 100%, and the K of a weak acid, which only ionizes to a very small extent. In fact, most weak acids ionize at a rate of 10% or less. 10% is kind of that benchmark number there. Nearly all of them are less than 10%, and quite a few of them are much less than 10%. So let's talk about weak acids then in more detail and this equilibrium constant, which we will now name. So most acidic solutions are weak and therefore are only partially ionized in solution. The ionization reaction is an equilibrium one in which a water molecule receives a hydrogen ion from the acid. Okay, we're talking about Bronsted-Lowry acid-base theory here. Remember, acids are proton donors or hydrogen ion donors, and bases are hydrogen ion or proton acceptors. So this is what's going on when you take an acid and dissolve it in water. All right, the acid donates a hydrogen ion or proton to water. So here's our acid, here's our base. All right. Now the base once it receives a hydrogen ion, what's formed is its conjugate acid. A little review here on Bronsted-Lowry acid-base theory. So this is our conjugate acid here. Remember, those are an acid-base pair. What's left behind from the acid, once it donates a hydrogen ion or proton, is called its conjugate base. And so the cyanide ion would be its conjugate base, and their HCN and the cyanide ion would be our other acid-base pair. All right, little review there. This is what actually happens when an acid is dissolved in water and undergoes dissociation. All right. Again, I'm gonna, just like we did back in Unit 11.1 with the self-ionization of water. Remember, we had a real version and we had a shortened version. We're gonna do the same thing. So this is the real version. This is what actually happens when an acid dissociates in water, in the presence of water. But just like with the self-ionization of water, this reaction can also be expressed in a more simplified dissociation version, which is just showing the splitting of the weak acid molecule into its ions. All right, so this is the short version. Whereby our hydrocyanic acid is just dissociated into a hydrogen ion and a cyanide ion. If you compare the two reactions, and you don't have to write this down, but I'll go ahead and write it. So here was the real one. Here was the real one. All right. Notice that, so here's our acid here. So our cyanide ion is the same, all right? The only difference here is, this is what really happens. We get the formation of a hydronium ion. In our short version, we're showing the formation of a hydrogen ion. Remember, all a hydronium ion is a water molecule that has a hydrogen ion attached to it, all right? So these two equations, equilibrium equations, are describing the same reaction. Just remember, this is what really happens. This is just a shortcut way of writing that. Either one is okay. All right? Either version is okay. Again, for simplicity's sake and to save time, in most texts, once this is explained, everybody uses the short version, myself included. But I want you to understand that that's what really happens. All right. The equilibrium expression is written like all other ones, and K now is called Ka, or the acid dissociation constant. So what does the value of K tell us in regards to acids? Right here. We kind of alluded to this when we were talking about this, all right, this chart. The K for a strong acid is infinitely large, all right? They're huge. But the Ks for all weak acids are fairly small, all right? And so what does that mean? Well, the magnitude or value of Ka indicates the tendency of the hydrogen atom to ionize, all right? And thus, the larger the value of Ka, the stronger the acid. Pretty simple stuff there, all right? The bigger Ka's value is, the stronger the acid is. Because a measure of acid strength is to what degree it dissociates or ionizes when dissolved in water. The 7 strong acids ionize 100%. Their Ka values are so big, we can't mathematically define them, all right? All the rest of them, we can. Okay? All right, so let's look at our first example here. There we go. Okay. we go. A student prepared a 0.100 molar solution of formic acid, all right, 0.100 molar, HCHO2, and measured its pH with a pH meter. The pH at 25 degrees Celsius was found to be 2.38, all right? We're going to calculate Ka for formic acid. All right, so first things first, we need to write our equilibrium equation. Again, we could write the real one, where the hydronium ion is formed when we add a water molecule to this acid, or we could write the shortcut version. I'm going to go ahead and write the short one. Again, just to save time, but I want you to understand the one that really happens. All right, so here's formic acid, HCHO2, AQ, in equilibrium with the hydrogen ion. And, well, when you pull a hydrogen ion off here, what's left is the formate ion, CHO2 negative 1. The nice thing about acid dissociation is you're pulling off a hydrogen ion, all right, 1, and so what's left behind after you pull that away is going to have a negative 1 charge. As you can see, our acid, our hydrogen ion, and in this case our formate ion, are all in a 1:1:1 mole ratio, which really simplifies things. So that's kind of an advantage to Ka, all right? So let's do a Lysch chart here. Okay. And we have a 0.100 molar solution of formic acid. Initially, of course, our hydrogen ion and our formate ion are 0. We know that our reactant disappears and our products appear. And it's like, okay, well, what else do we have? Do we have anything? It might first appear that we don't, but in reality, we do. We do, because we have, once this solution was done, this reaction has gone to completion, we have a pH, all right? Think back to Unit 11.1 on acids and bases. What is pH? Well, it's a way of measuring the hydrogen ion concentration of an acid. So this pH value is very valuable to us, all right? So at equilibrium, the hydrogen ion concentration is equal to 10 to the negative pH, or the inverse log of the negative pH. Got to remember that that relationship there. And so this, and we have that pH. So it would be 10 to the negative 2.38 power. And so our equilibrium hydrogen ion concentration to 3 sig figs would be 4.17 times 10 to the minus third. However, if you remember, we do not do any rounding within an ICE chart, all right? So we don't do that till we get to the end. So I'm not going to round it yet. 4.16, 869, 3835 times 10 to the minus third molar. And that then would go right here. 4.16, 869, 3835 times 10 to the minus third. Same thing with our formate ion, because they're in a 1:1 mole ratio. 4.16869, 3835 times 10 to the minus third. Of course, our change there is the difference between that and 0. So again, same number. 16869. I should have this memorized now. Minus third. Same over here. And if we know these changes, we know this one too, because they're all in a 1:1 mole ratio. So this would be minus 4.16869, 3835 times 10 to the minus third molar. All right. The Just remember, just a little reminder there, 1 to 1 to 1 ratio. And that's kind of the beauty of Ka, is we have this 1 to 1 ratio throughout. And now we just subtract this from 0.100 molar. And again, I'm not going to round that yet. 0.095831. 306. And there we go. And we want to calculate Ka. Okay, so let's write our K expression. So Ka would be equal to, it's like any other K, products over reactants. Since we're all in solution here, they all get used. So we have our hydrogen ion concentration times our formate ion concentration over our formic acid concentration. These two numbers are the same, 4.168693835 times 10 to the minus third, so that would be simply that squared, so we don't have to write it again. And our acid concentration at equilibrium, 0.095831306. And now we can round to 3 sig figs based on our data there. And Ka comes out to be 1.81 times 10 to the minus 4. 1.81 times 10 to the minus 4, which is fairly small. All right. All right. Now, what percentage of the acid is ionized? Okay, well, let's take a look at that. So, we started out with 0.100 molar, all right, and we ended up with 0.095831306 molar because it ionized by this amount right here. So any of these numbers here basically would help us to solve this. But we technically look at what quantity of hydrogen ions were produced at equilibrium. All right. So the percent ionization of a weak acid is equal to its equilibrium hydrogen ion concentration, over its initial acid concentration, which in this case is formic acid, times 100. Okay? All right. And so 168693835 times 10 to the minus third over 0.100 times 100 to put it into a percentage. And for that, at 3 sig figs, we get 4.17%. All right? So what does that tell us? Well, formic acid only ionizes 4.17%. So what does that mean? Well, that means that at equilibrium, 4.17% of these formic acid molecules dissociated or ionized, and 95.83% of them remain intact. Okay? And that is true of all weak acids. They only ionize to a small degree. Okay? Small degree. All right, let's go on to the next one. This one's very similar, but it asks a little different question. All right, let's scoop that up just here. There we go. All right. Here now we're going to calculate the pH of a 0.20 molar solution of hydrocyanic acid, HCN, And the Ka for HCN is given at 4.9 times 10 to the minus 10. Now, that's pretty dang small. By the way, as I'll refer to this chart again, the Ks for various acids and bases are listed on here. Is HCN on there? Well, I don't see it right off the top of my head. Oh, there it is. Yeah, down towards the bottom here. They listed at 4.0 times 10 to the minus 10. The figure I took from my textbook, a little bit different, I guess. So apparently the conditions must have been a little bit different. So anyway, so let's take a look at that, shall we? So let's write our equilibrium equation first. So we have HCN in equilibrium with its ions, the hydrogen ion and a cyanide ion. Again, everything's 1 to 1 to 1. So we have a nice chart here we'll set up. So initially, we have a 0.20 molar HCN. Our ions, of course, initially are 0. And then, okay, so before, on our previous problem, we were given a pH of the solution, which meant that at equilibrium, we actually were able to determine a value of our hydrogen ion concentration at equilibrium, which then allowed us to figure out all the changes and all the other equilibrium concentrations. We don't have that luxury this time. We don't have that. So it appears then we're going to have to go back and use X as our change. We don't know what it is. We know that this goes down by some value X. These go up by some value X. And at equilibrium then, we would have 0.20 minus X molar X molar X molar. And I think I'm already, let me hear. Oh yeah, I'm already hearing some groans out there amongst the audience. All right. When this happened before, been a while, you've been a week or so's worth of lessons ago, when we were presented with a situation like this, what did we have to do to solve for X? Yeah, you're right. The dreaded quadratic equation. Yeah. Well, not so fast, my friends. We have some good news. We can make the simplifying approximation that X, the amount of acid that dissociates, is small in comparison with the initial concentration of the acid, since Ka for weak acids is small. All right? If the value of K is small, then that means at equilibrium, the values of the concentrations of the ions are going to also be very, very small in relation to the concentration of the original acid. And so here's how we can make this simplifying assumption, all right? If, big star here, if Ka, all right, has a value of 10 to the minus 4 or smaller, then we can make this assumption and eliminate the need for the quadratic equation. But we can do that only if you make a qualifying statement. So only if you say X is small as compared, all right, to the initial acid concentration, whatever that might be. All right? So I'm going to explain that here right now. Our value of K is 4.9 times 10 to the minus 10, which is extremely small. It's a million times smaller than that. All right, it's 6 decimal places smaller. And so we can make that qualifying assumption here. So what we're saying is this value of X here as compared to this concentration here is negligible. All right, it's so small that it's meaningless. And so by making this statement right here, and I'm going to be more specific now, X is small as compared to 0.20 molar. With that statement right there, we can get rid of that and get rid of that. And that, my friends, is a beautiful thing because that just eliminated the need for the quadratic equation. And let me show you how. So our Ka is equal to the hydrogen ion concentration times the cyanide concentration over the HCN. All right. We have a value of Ka, 4.9 times 10 to the minus 10. All right. These are both X, so that would be X squared, X times X. And now, with this X scratched out, we now have 0.20. If that had been 0.20 minus X, then think back to what we'd have had to do. We'd have cross multiplied here, multiplied this out, 0.20 minus X. We'd had to FOIL it and then set it up in ax squared plus bx plus c mode and use the quadratic to solve for X and then determine which X was reasonable and which one we could throw out. But with that minus X not being there, and we cross multiply, we have 4.9 times 10 to the minus 10 times 0.20 equals X squared. No need for the quadratic there, folks. Just multiply these two numbers, square root it, we got it. Simple. Done. And X then to 2 sig figs is 9.9 times 10 to the minus 6 molar. So what does that tell us? Well, it tells us right here. So our equilibrium hydrogen ion concentration, which is the same as our equilibrium cyanide concentration, are both equal to 9.9 times 10 to the minus 6 molar. 9.9 times 10 to the minus 6 molar. All right? And our equilibrium hydrocyanic acid remains 0.20 molar. Since we eliminated this, we disregarded it. Now let me do a quick calculation here. Let's just say, for the sake of argument, that we hadn't scratched that out. I can give you an approximation what this would be without using the quadratic by simply subtracting this out of here. 0.20 minus 9.9 exponent negative 6. All right. This, if we had done that, this would be 0.1999901. To 2 sig figs, what is 0.1999901 molar? Well, the 2 sig figs, it's still 0.20. And that's why you can do that. That's why you can do that. If K is small enough, then this value of X is going to be small enough so that you can disregard it in comparing it, the equilibrium value of the acid concentration to its initial value. They will be essentially, rounding-wise, significant figure-wise, the same. Okay? That is most definitely good news. Anytime we can eliminate the need for the quadratic equation, that's a win. All right, that's a win. So we need to calculate the pH. So we're not quite done yet. All right. So the pH, we solved for pH before in unit 11.1. Negative log of the hydrogen ion concentration. All right. That, of course, would be the equilibrium hydrogen ion concentration, since initially it was nothing. And so we have that value right now. Negative log of 9.9 times 10 to the minus 6. And the pH then at equilibrium to 2 sig figs is 5.0. 5.0. Okay. Which is still acidic, all right? Somewhat acidic. It's not ridiculously acidic, but this is why. It's a weak acid, right? It's a weak acid. They're not going to be very, very low pH, right? All right. Well, I think that takes care of today's lesson over Ka, the acid dissociation constant for weak acids. Remember, the K for strong acids is so large that we cannot mathematically define it. Okay? That was this then, a lesson would allow you to complete our assignment, which was equilibrium number 8, weak acids in Ka. That would be your assignment for this lesson. And when we come back next time, we will look at a very similar scenario with weak bases. So until then, this is Mr. Keister signing off. Everybody take care. Have a great day. Stay safe, and we'll catch you next time. So long, everybody.